Right. Hello everyone. I'm Vamsi, faculty at IISc, and I work in this area of mathematics called differential geometry. Uh, I mean, we've heard some wonderful talks in biology and physics, and unfortunately, my topic is far more technical. I hope to make it as accessible as I can. So let's see how unsuccessful I'll be. So the bottom line is the following. The one major theme of my research is about partial differential equations. Basically, it's just equations involving derivatives. Now, when a physicist or an engineer thinks about differential equations, they perhaps think about how to solve them by explicit formulae or how to cleverly simulate them on a computer and get approximate answers. But when a mathematician thinks about partial differential equations, she or he usually refers to theology. In other words, the central questions are about existence and uniqueness, rather than the ability to actually find out the solution, because you can write innocent looking partial differential equations that you can prove do not have solutions. Forget about being able to cleverly finding a nice formula for them. You can prove they don't have solutions at all, right? So this is a more fundamental question than what most people are used to, yeah? So the equations that I study come from geometry. And again, when you think of geometry, you probably think of high school level geometry about triangles and so on. It's not quite that. It's a more fancy version of that called differential geometry. And this is just a line for the sponsors. I mean, I claim it's connected to physics, but there's a physicist in the audience, so I hope they don't take me too seriously. I shall only talk about two such partial differential equations in this 15 minutes or so. So in both of them, I and my collaborators proved that solutions exist. As I said, the point is to prove that solutions even exist, right? It's like theology. And this is, of course, a hard task. How do you prove something exists out of nothing, right? That's hard if and only if certain quote unquote easy to check conditions are met. I say quote unquote because they're not really that easy to check, but they're certainly easier than not having anything at all. If you will, they are like algorithms, but again, quote unquote algorithms, not really algorithms in the sense of computer science. And for the experts, these are called Kobayashi-Hitchin correspondences, or to be politically correct, Kobayashi-Hitchin, Donaldson, Uhlenbeck-Yau correspondences. This field is minefield. Anyway, this is the tip of the iceberg. Hopefully, similar results can eventually help not only with physics, if they can actually help with physics at all, but more importantly, they can help with an area of mathematics called algebraic geometry. And some words for the experts, moduli spaces, in case you know what they are. There have been several instances, and to be very presumptuous, my work is not even close to being in the same galaxy as this, but the Poincare conjecture is the most famous among these sorts of instances, where theorems in different fields had been proved using partial differential equations and differential geometry. Okay, so this is the bottom line, a high-level overview of what I'm going to talk about. All right. Okay, so let me give you an example of a partial differential equation. And again, I'll be a hypocrite. I won't actually write down the partial differential equation and bore you more than I already am. So this example comes from differential geometry. It's called the uniformization theorem. The theorem is that this partial differential equation has a solution. That's the theorem. So it states that every surface has a metric whose curvature is a constant. Now, right at the top of the bat, I can't define these things without going into details, but roughly all of us know what surfaces are, right? I mean, we see them in real life. What is a metric? A metric is simply a gadget used to measure distances and angles on a surface. For example, if you take the surface of the Earth, if you want to know the distance between Vizag and Hyderabad or some such thing, you would need to, I mean, this very question, the answer to such a question involves a metric. Okay? Now, given a metric on a surface, you can talk about the curvature of a surface. For example, the Earth is a curved thing, right? I mean, hopefully all of us agree. And the Earth, if you assume it's a sphere, a perfect sphere, its curvature is a constant. In other words, wherever you go, the Earth is equally curved. Now, this is for a surface like the Earth, right? That does not have any holes in it. Now, if you take a surface that has a hole, I mean, like a donut or a vada, depending on your culinary taste, it has a metric whose curvature is 0. If you have 2 holes and higher, there's a metric whose curvature is negative, whatever curvature means, really. Now, the bottom line is that this particular theorem involves solving a PDE. Unfortunately, I haven't written down the PDE. Basically, curvature is something that depends on 2 derivatives of the so-called metric. Yeah. Okay, so coming to our work, this is a collaborative work with a bunch of chaps. So the early universe, and here I hope the physicist does not, in the audience, does not take me too seriously. So the early universe was presumably akin to a magnet getting demagnetized. In other words, what's a magnet? It consists of a bunch of tiny magnets that we call domains, and between any 2 domains, you have these so-called domain walls. And when you get demagnetized, you have lots of such domain walls, in that the tiny domains point in different directions, and defects like domain walls were created. Okay, this is just still conjecture. I don't think any of these defects have been observed in practice. So the defects we are interested in are defects in gravity, just akin to this magnetism thing, but with gravity. That is, these things called cosmic strings that are different from the strings in string theory that Professor Spentavadia alluded to. So these cosmic strings are governed by complicated partial differential equations. They involve Einstein's equations of general relativity and equations that study the other 3 forces of nature, electromagnetism or strong nuclear or weak nuclear force, and so on and so forth, depending on the kinds of things you look at. Anyway, the bottom line is these equations were they were generalized by us, and we came up with these so-called gravitating vortex equations. Now I have to throw in some technical words for the e-experts. So we are on a compact Riemann surface equipped with a holomorphic line bundle, and you have a holomorphic section. If you give me all of this data, the question is find a metric on the line bundle and a metric on the Riemann surface such that first equation, which is an equation for the curvature of the metric, is met, and likewise for the curvature of the Riemann for the metric on X. Okay, so these are partial differential equations. All right. So these equations do not always have solutions. That's a problem. Okay. There are 2 equations. Even if you fix this G, and if you want to solve the first equation, that is, you want to find an H that solves this equation, or G, let's say, even then you don't have solutions. Okay. There's a very well-known obstruction for the first equation. The first equation is known as the vortex equation. Originally, it came up in the context of superconductivity in physics. At least an avatar of this came up in that context. So it does not always have solutions, and there's a very well-known obstruction. I mean, you can quantify how badly you failed to solve this. And that equation is, for the experts about the first Chern class, it's related to the stability of a certain vector bundle. We identified, what we did new is that we identified another obstruction in the case of the Riemann surface being the sphere. For both of these equations together, this obstruction is an example of what's known as a Futaki invariant, in case you know what that is. For higher genus, namely if you have more holes, a badly cooked vada, for instance, then we proved that if the first equation can be solved and this coupling constant is very small, then a unique smooth solution exists. Okay, so that's what we did. For the sphere, we proved that these equations have solutions if and only if some quote-unquote easy to check conditions are met. Again, for the experts, they're just GIT stability of the divisor, phi. Okay. All right. So let me go to my second set of equations. So again, these are quote-unquote motivated from physics. So Professor Spentavadia mentioned something about the ADS-CFT correspondence. It's some sort of a correspondence between two different, if I may use the word, different areas in the same subject, right? Akin to that, there is a conjecture called mirror symmetry in string theory, motivated from it, but not really connected to it. And from an area of maths called Chern theory, and a very famous conjecture that was solved in the 70s and 80s called the Calabi conjecture. I came up with a certain PDE for certain differential geometric gadgets called a Monge-Ampere equation. In the special case, so in a very special case of a vortex bundle, and the name vortex is not a coincidence, it's very closely connected to the vortex in this slide. These two words come from the same source. So it boiled down to an equation similar to the above, and in this case, it's a single equation. There it was two equations. And we get this horrible, horrible looking equation. For people who are interested, I'm sorry, but the point is, this equation is actually, while it hides many things, it's a second order equation. This thing depends on two derivatives of this h. This thing depends on one derivative. And here we have no derivative dependence, but it's a highly nonlinear second order equation. Okay? So linear equations are somewhat easier to study, but this is highly nonlinear. And it's a beast in its own right. And it depends on two numbers, R1 and R2. These are integers. Okay. So what I proved was that a unique smooth solution exists. So if a solution exists, then it's unique. There's only one of them. If and only if R1 is larger than R2. So this is a very easy to check condition. All you need to give me is two integers, R1 and R2 greater than or equal to 2. If one of them, R1 is larger than the other, then you have a unique smooth solution. Otherwise, you don't. Okay. Now, surprisingly enough, well, it won't be a surprise if you haven't seen partial differential equations, but for most for most people who have seen these sorts of things, usually it is easier to prove uniqueness. That is, having a single solution is easier to prove than having a solution at all existence. Okay, usually. But in this particular case, uniqueness was way harder. I mean, maybe I was just being dumb, but I think it was way harder than existence. Okay. All right. So looking beyond, this is not the end of the story. There are miles to go before I sleep. So I spoke about uniqueness, right? But I never said anything about uniqueness for this set of equations. I said a unique smooth solution exists when you have two holes or more. What about for the sphere? Well, the answer is we have absolutely no idea. So uniqueness in the case of a sphere, that's completely open. And actually, these equations are themselves special cases of these so-called Kähler-Young-Mills equations. So I would want to study those also in the future. Then the second set, PDE, is a special case of vector bundle Monge-Ampere equations. I would want to study that also. And it's and related things like consequences of it, like Chern class inequalities and perhaps the deform Hermitian-Young-Mills equation and so on and so forth. Okay, so I think I'll stop at this point. So yeah, please.
Thank you very much, Vamsi, for a very nice talk and clear. Also making effort to connect these two ideas in physics. We do have a question for you, and
Sure.
the question is from Professor Bhaskaran. He says, a very nice talk, Vamsi. Physicists often find useful approximate solutions when mathematicians say that no solution exists. How do these approximate solutions fit in your scheme?
I'm not sure. Physicists do find approximate solutions when solutions do exist, but perhaps what the professor means is solutions exist, but you can't write a nice formula for them. But if you can prove that solutions don't exist, I'm not sure what it means to find an approximate answer. It's like saying square root of -1. You can't approximate it because it doesn't even exist as a real number. So yeah, I mean, I'm not entirely sure of the question, but yeah, this is my take on it.
Maybe I can respond to that. So,
Sure.
what physicists would do or try to do then is to find a region where solution does exist, which is nearest to the given problem, where solution doesn't exist, and try to approximate it.
Possibly. Maybe you change the differential equations itself by adding a few small parameters or something, perhaps.
Parameter space.
That's true. Yeah, I mean, as I said, as Professor Bhaskaran, I guess, or Balakrishnan, I don't, I can't see the chat, but he said I'm a pure mathematician and indeed guilty as charged.
That's right. Okay, all right. So I don't see any other questions on YouTube or on the WebEx here. So thanks once again, Vamsi, for a very clear presentation.
Thank you.